Seems like we're doing fine. Okay, cool. Thank you. So what are we going to do today? Today, we will do a little strong induction. And then we'll start chapter 4, which is number theory and modular arithmetic. Okay, so strong induction. Can someone remind me what some idea about strong induction is? What's going on with strong induction? The centipede drawing. I'm glad that that is sticking with y'all. Yes, exactly. So for strong induction, you have a base case, which we think of as P1, and then the inductive step is we assume P of 1 all the way up through P of K and use these to prove P of K plus 1. Exactly. So you use all of the previous steps, or at least you have access to all of the previous steps. So I don't think I actually did an example last time. There aren't very many fun examples that I have of strong induction, so I have 2 examples, and that'll be good enough before we move on to the next section. Okay, so here's one example. Prove that all postage of value higher than 18 cents. Is this the cent symbol? I'm not sure. 18 cents. I wonder if I know how to do pounds or something. Anyways, 18 cents can be made out of 4 cent and 7 cent stamps. Okay, so what we should first do is, before we try to prove anything, we should kind of play around and see what's going on. So for instance, are there values less than 18 that we cannot reach by just using 4 cent and 7 cent stamps? Like what? Okay, here are definitely some numbers that we can hit if we have 4 and 7 cent stamps. We can definitely get 4. We can definitely get 8. We can definitely get 12. We can definitely get 16 just by taking 4 cent stamps. Yeah, we can't hit 6 cents for sure, right? Because there's no way if I have 2 4 cent stamps, then I'm too big. If I have 1 7 cent stamp, then I'm too big. So I can't get those. Exactly. 1, 2, 3, 5, 6, I can't hit. I also can't get 17, right? 17 can't be hit, but 7, 14, then I can start adding them together, right? 7 plus 14, or 7 plus 4 is 11. So here are some of the numbers that I can reach, but there are definitely gaps. But let's examine the following thing. Let's look at 18. Can I get 18 as a sum of 4 cents and 7 cent stamps? Yes, I can. This is equal to what? Two times 7 plus 4. So that's cool. Exactly. How about 19? Can I get 19 out of 4 and 7 cent stamps? Yeah, exactly. 19 minus 7 is just 12. So 19 is equal to 3 times 4 plus 7. Cool. How about 20? Oh, well, yeah, 20 is divisible by 4. 5 times 4. And then 21 is 3 times 7. Ah, I have 4 numbers in a row, all of which can be written in terms of 4-cent stamps or 7-cent stamps. I claim that now I should be able to get everything past this. Can someone kind of see why? For instance, why do I know immediately that I can write 22 as a sum of postage using 4s and 7s? Yeah, exactly. Because 22 is just 18 plus 4, so I take whatever expression I had for 18 plus a 4-cent stamp. What about 23? Well, 23 is just 4 bigger than 19, so I can take whatever postage I had for 19 and add a 4-cent stamp. Same for 24. 24, okay, on one hand, I can just think of it as this is divisible by 24, that's great. But another way to say it is this is 4 greater than something that I already know is possible. So I just take my expression for 20 and add a 4-cent stamp. And the same process can go for any higher number, right? Any big number up here, like 107, I'm going to be able to subtract off copies of 4 until it lands on something in here, right? Don't ask me which one it actually lands on, but 107 is equal to 4 times k plus either 18, 19, 20, or 21. And then I just take my expression for one of these and add the correct number of 4, oh, you can't see, the correct number of 4-cent stamps. Does this kind of make sense? This is the idea behind the induction. Yeah, this is going to be what we do to kind of this is the idea behind the proof. I think oftentimes the proofs are written in kind of a formal language, and it's good to kind of play around with examples before you write things up. Examples are very good. Okay, so now let's actually do a proof of this fact by strong induction. Now, there probably is a way to do this by normal induction, but what exactly would your normal induction be? So for instance, you've shown, maybe you have 4 base cases, P of 18, P of 19, P of 20, P of 21, and then you want to show P of k plus 1, assume P of k. Now show P of k plus 1. So this is saying if you know for k greater than 18, greater than or equal to. So knowing that I can express k as a sum of 7s and 4s doesn't immediately mean I can express k plus 1 as a sum of 7s and 4s, right? I'm not saying that normal induction won't work, but normal induction will require quite a bit more work. Right. But strong induction, as we will see in just a moment, so proof. We use strong induction. Base case, here we'll actually do base cases. P of 18, P of 19, P of 20, P of 21. right? We checked all of these over here. We can write 18, 19, 20, and 21 in terms of 4 and 7 cent stamps. So 18 is equal to 2 times 7 plus 4. P of 19 is equal to 7 plus 3 times 4. 20 is equal to 5 times 4, and 21 is equal to 3 times 7. Okay, we already did this. Now my inductive step, what I will now do is I will assume that P of, what do I want to do? P of L holds true for L is equal to 18, 19, all the way up to K, where K is greater than or equal to 22. So my K is now bigger than all of my base cases, and I'm assuming that the proposition holds for all the numbers in between 18 and K. So for all integers 18 less than or equal to L less than or equal to K, P of L, assume P of L. And here, K is greater than or equal to 22. Now we want to show P of K plus 1. And now the point is, I don't want to just rely on my knowledge about P of K. I want to rely on my knowledge of P of K minus 3. By our assumption on K, K minus 3 is greater than or equal to actually 19. Thus, P of K minus 3 is true by the inductive hypothesis. But then K minus 3 is equal to A1 times 7 plus A2 times 4, with A1, A2 in Z greater than or equal to 0. So K plus 1 is equal to A1 times 7 plus A2 plus 1 times 4. This completes the inductive step. Thus, all postage greater than or equal to 18 is achievable. So once again, the point of using the strong induction is that if I'm trying to prove P of K plus 1, it's much more helpful that I examine the statement P of K minus 3 instead of P of K. So we use strong induction. Any questions here? No questions? Everyone's comfortable with postage? I actually sent out some mail recently. I had to go to, why is K bigger than or equal to 22? That's an assumption that I can make. I could do K greater than or equal to 21. The point is that 21 is already covered in my base case. And also, if K is equal to 21, then subtracting 4 from 21 leads me back to 17, which I can't do. So I want to do things that are bigger than my base cases so that I fall back into the base cases. If I pick 21, then I fall back to a P of 17, which is false. Cool. Okay, shall we do another? How I got the equation for k plus 1. You mean this? This is exactly this expression. So if I say the number k minus 3 can be written in terms of 7 postage stamps and 4 postage stamps, 7-cent postage stamps and 4-cent postage stamps, that means k minus 3 can be written as some multiple of 7 plus some multiple of 4, right? So are you okay with this expression, k minus 3? So all that I do is I know that k plus 1 is equal to k minus 3 plus 4. So what I really just did is I added 4 to this expression. But adding 4 just means I can rewrite the number of 4s as this number plus 1 more. It's exactly the math, or yeah, behind the idea of if I know how to write 20 as sums of 7s and 4s, then I write 24 as whatever that expression for 20 was plus a 4-cent stamp. And this is just one way to write it down. Cool. Any further questions? It seems no. So let's do another example. And before I do this example, I have to tell you a little bit about primes. Primes. Okay, what is a prime? Well, I don't want to talk about divisibility. There's a better definition of prime than the one that I'm about to write. But a prime in the integers is a number p whose only positive factors are 1 and itself. A number which is not prime is composite. Yes, a number that has only 2 factors. You want to be careful to exclude negative factors if you want to use that definition. But I did that. Only positive factors are 1 in itself. 1 is not a prime, so 1 is composite. Yeah. So we should exclude 1. A prime in Z is a number P greater than or equal to 2. 1 should be thought of as not a prime for sure. And so if you define composite as not a prime, then 1 is composite. The important thing is to know that 1 is not a prime. Right. I reserve the right to change my mind later about whether or not 1 is composite, but I will never change my mind on 1 not being prime. Okay. Let's continue. So what I want to show is the following. Show that n greater than 1 can be written as a product of prime numbers. This is called the prime decomposition of a number, and I think it's pretty familiar. This is like saying 6 is equal to 2 times 3. You can rewrite 6 as a product of primes, or I don't know, 51. This is probably going to be equal to 3 times how do I divide 51 by 3? Someone help me. 3 times 17. Perfect. Help. Okay, so we want to be able to write positive integers as product of only primes and only have prime numbers remaining. Okay, and so the way that we're going to prove this is via induction. So our base case is P of 2. Can 2 be written as a product of primes? 2 can be written as a product of primes. Namely, it's just 2. By the way, the reason, or at least a reason, there are many reasons, but one reason for not including 1 as a prime is that you want uniqueness of this decomposition as a product of primes, but you can always multiply any number by 1 however many times you want, and it'll be the same number. So that would destroy uniqueness of a prime decomposition. There are even better reasons for not including 1 as a prime, but that's one of them. Okay. So now what I assume is my inductive hypothesis is the following. P of L for 2 less than or equal to L less than or equal, less than or equal to K. So that is, I'm assuming 2, 3, and all the numbers up to K, all of these numbers have a decomposition into primes. Each of these numbers can be written as a product of primes. Now I wish to show P of K plus 1. Probably units should not be considered composite. Maybe y'all are right. I'm coming, I'll have to think a little bit more about what we think of 1 and -1 as. Okay, in any case, right. Let's examine K plus 1. There are 2 cases. What are my 2 cases? Prime or composite, exactly. Case 1, K plus 1 is prime. Then K plus 1 is equal to K plus 1 is an expression for K plus 1 as a product of primes. So P of K plus 1 holds. Case 2 is K plus 1 is composite. So K plus 1 being composite means it has positive factors that are in between 2 and K plus 1. So exist 2 less than or equal to A less than or equal to B less than or equal to K plus, or not equal to K plus 1, less than K plus 1, such that K plus 1 is equal to A times B. So then, since A and B are inside here, by the inductive assumption, by the inductive hypothesis, P of A holds and P of B holds. So for instance, A can be written as some product of primes P I1 to the, how do I want to write this? P1 to the A1 dot 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 PL to the AL. L is bad, M. And similarly, B is equal to Q1 to the B1 all the way up to Qn to the Bn. Here I'm just saying A and B are products of primes. So P's and Q's are primes. But then K plus 1 is equal to A times B is equal to this product of primes, P1 to the A1 all the way up to PM to the AM times Q1 to the B1 all the way up to Qn to the Bn. Thus, K plus 1 can be written as a product of primes. This concludes the inductive step. Thus, positive integers, thus n greater than or equal to 2 has a prime decomposition. How do we feel about this? Maybe a little uncomfortable because I haven't really been talking about primes, but yeah, this is a much this is a place where you see that strong induction is really actually doing work, right? Like for the stamp one, I could probably finagle a way to do it by induction, regular induction, but this one you really see it's really using strong induction in a nice way, because if your number k plus 1 is not prime, it's composite, and so its two factors kind of land back into our inductive hypothesis, which is nice, I think. Any further questions? Okay, despite not doing very many examples for you, I think I'm already done with induction and strong induction. So these are the last of the proof techniques that we will need in this class. The first part of this class was really devoted to logic and proof techniques. And we went through a lot of different proof techniques and why they're logically valid. And with induction and strong induction, we kind of finish off that part of the course. And the rest of the course is going to be kind of applying these proof techniques to a lot of different topics. Starting with arithmetic, reading, writing, arithmetic. Any questions before I move on to a different chapter? Okay. Chapter 4. This is the chapter on number theory and modular arithmetic. And we'll only be doing sections 4.1 and 4.3, I think. So it's pretty short. Let me just check the book really quick to make sure. Yep, just those two sections. Okay, definition. So for this entire chapter, we're going to be working in Z. Okay, so definition, let A and B be integers. You've already seen this one before. We say that A divides B, and we write it as A with this line B, A divides B, if what? Yep, if there exists a K in Z such that B is equal to AK. Thank you, yes. Now let's do a little lemma, which will allow us to, I mean, this is just a very easy lemma, but it's helpful. So part one is if A divides B and A divides C, that implies A divides B plus C. Two is if A divides B, then A divides BC for all C in Z. And three is that if A divides B and B divides C, then A divides C. And the proof of this is very easy. So much so that I'm going to let y'all do it. What's the proof of one? Yeah, exactly. By assumption, B is equal to K1A and C is equal to K2A. So B plus C is equal to K1 plus K2A. So thus A divides B plus C, because B plus C can be written as an integer times A. Great. For 2, it's nearly just as quick. B is equal to AK, so BC is equal to AKC, so A divides BC, because BC can be written as KC times A. And then 3 is this one. How do I do 3? Y'all tell me this one. If A divides B, then B is equal to AK. And if B divides C, then C is equal to, let's say, BK2. So C is equal to BK2, which is equal to A K1 K2. Thus A divides C. Yeah, perfect. Thank you, Catherine. Okay, these were easy. And a corollary of all this is that if A divides B and A divides C, then A divides Bm plus Cn for any m and n in Z. So this is saying if A divides two integers, then it divides all, these are going to be called linear combinations of those integers. And this is easily deduced from this lemma. Okay, so this is just kind of getting us started on what divisibility means. By the way, now I can give you the better definition of prime. This doesn't fit with what we're discussing right now, but better definition of prime. P is prime if P dividing AB implies P divides A or P divides B. It's probably not immediately clear why this is the same as the definition that we were talking about on the other page, but this is actually the better way to think about primes. And we can check, for instance, in this example, that, for instance, 6 is not prime. Can someone bring me a counterexample for why 6 is not prime in this language? That's fair. It is a bit confusing, but I think that if we do a couple examples, it'll become more clear. Here's a reason why 6 is not prime. 6 divides 6, or maybe I should say 6 divides 2 times 3, right? But 6 does not divide 2, and 6 does not divide 3. The point is that, right, exactly. That's one way to think about it. Another way to think about it is something like, if, let's say that we have something that is a composite, so P1 times P2. This number will always divide a pair of numbers where, let's say we have P1 and some stuff over here, and we have P2 and some stuff over here, but P1 doesn't appear here, no P1 and no P2 here. The point is that if you're not a prime, then you can kind of pull different factors from different places without actually dividing either one of the full factors. So if you play around with this idea, you'll quickly see that any number which is not a prime, you can immediately contradict this statement just by dividing itself, actually. I agree that it's a little confusing, and I'm not claiming that this is clear. I'm just claiming that this is a definition that is a good one. And if you play around with it, you'll see that it recovers your intuition around primes over Z. Any further questions about this? I admit that I'm not about to talk about this. This is going to be some 4.3 stuff. I'm about to talk about modular arithmetic. Where do I have 1? I don't think I have 1 anywhere. Where do I have P dividing 1? So my counterexample for why 6 is not prime is that I was able to find a product of two terms such that 6 divides the product, but it doesn't divide either of the factors. On the other hand, if 3 divides some product, like someone give me a number that 3 divides. Right, exactly. If 3 divides, I don't know, 12, what are all the ways of writing 12 as a product of two primes? Or sorry, as a product of numbers. We could write 12 is equal to 1 times 12 or 2 times 6 or 3 times 4, right? These are all the different ways I have of writing 12. Then if I have 3 dividing 1 times 12, I actually have 3 dividing 12. So 3 divides one of the factors. If 3 divides 2 times 6, well, actually, 3 divides 6. 3 divides one of the factors. And if 3 divides 3 times 4, well, then 3 divides 3. 3 actually divides one of the factors. All of the possible ways to write your given number as a product of two factors, if a prime divides it, it has to divide one of the factors entirely. There's no way to split it up in between the two factors, basically. Now, does this kind of, are you starting to see why this is a reasonable way to think about primes? Cool, I'm happy to hear that. Not what I actually wanted to talk about, but cool nonetheless. So I'm happy about that. Okay, so next, theorem. This is the division algorithm. This basically says we cannot divide in the integers. We cannot divide on the nose in the integers. The best that we can do if we're trying to divide inside the integers is keep track of a remainder term. And this is very common from elementary school. So let a be an integer and d a positive integer. Then there exists unique integers q and r with 0 less than or equal to r less than d, such that a is equal to d times q plus r. So q here is called the quotient. D here is called the divisor, and R is called the remainder. And the proof of this goes through essentially strong induction. But I didn't want to do it because it's kind of boring. Maybe I'll give it to you as homework. Okay, this will take you back to the earliest math that you learned, probably. Let's do some examples. Let's say A is equal to 107. Now let's do something easy first. Let's say A is equal to 17 and D is equal to 5. Then what am I saying here? I'm saying I want to write 17. I want to express it as some multiple of 5 plus a remainder where the remainder has to be between 0 and D, and it cannot be as great as D. So my remainder has to be one of the numbers 0, 1, 2, 3, or 4. Yeah, that's correct. Boring stuff on the homework. This is why one becomes a math teacher, you know. You can write the fun math and leave the boring stuff for the homework. Okay, so what is the unique decomposition that we get for 17? What is 17 in this case? Yeah, 3 times 5 plus 2. So here, this is the dividend, or sorry, the divisor. This is the quotient, and this is the remainder. If you really want to remember how it goes, it should be something like this. Plus 2. Okay, another question, a slightly more interesting question. What about a is equal to negative 17? And d is still equal to 5. Then I get negative 17 is equal to what? Incoerto. That is unfortunately incorrect, Catherine, because what do I demand of my remainder? Yeah, I demand that my remainder be in between 0 and 4. It must be positive. So actually, negative 17 is written as negative 4 times 5 plus 3. So in other words, we're making bins, or this is the way that I see it. We're going right back to the number line. Here's 0, here's 5, here's 10, here's 15, and here's 17. So what this is saying is you go out here and you have some small number, this is the remainder. But when you go to negative 5, oh, I hope I have enough room, negative 10, negative 15, and then here's negative 20, and here's negative 17. The right answer is to go all the way down to negative 20 and then add 3. So this is how we get the uniqueness for this statement. Oh, you can't see. Okay. So this fact that the remainder is always a number in between 0 and the divisor is a very important part of what we're going to be doing with this circle of ideas. How about if I have A is equal to 17 and D is equal to 107? 17 is equal to what? Yeah, 0 times 107 plus 17. What about A is equal to negative 17 and D is equal to 107? Yeah, exactly. Now, negative 17 is going to be equal to negative 1 times 107 plus 90. Now I have a remainder of 90. So these keeping track of positive and negative and what influence that has on our division algorithm is important. Cool. Thanks for speaking up and participating today. It felt like a fun class today. I hope you all enjoyed some of the induction bits and getting into some number theory. Have a nice Friday, a nice weekend. Y'all should vote and get vaccinated. Get a flu shot. This is heading towards modular arithmetic. We're getting there. We're close.
Hey, Mark.
Yeah, sure.
Really fast, I'm sorry. Would you mind posting the midterm? The test anxiety was real and I accidentally didn't save the PDF.
Oh, yeah, sure.
Okay.
I might just send it to you.
Okay.
Yeah, I think I'll just send it to you, actually.
Okay, perfect. Thank you so much. Have a good weekend.
You too.